figured out that if you put this on a 1.8 degree tilt, you can get rid of this. Because now you can use the horizon to effectively create a wedge inside of this vessel. So your gas and liquid. So now the velocity of your gas at the front is much less. The velocity of the liquid is toward the back is much less. And where each of the phases is working for you, now it's more efficient. You can also hold more sand in here. And this is important because I'll talk to you about the math problem we had to figure out as a result. Continually improving the process is something that we're dedicated to. And as a company of, we've got probably 15 engineers, so a third of our company are all professional engineers. And we have people dedicated to just doing that. The other thing we like as an engineering company is data. Our clients seem to like it too, if they ever find the time to use it. But in that application of the verticals, you're blind. You don't know what's going on. What we started doing is putting this entire vessel on load cells. So we would jack it up off of this skid here, off of this metal base. We would screw up load cells, and now this entire vessel is being weighed at all times. So now you see it's, they work in kilograms, so I can't even give you a number. But they have, say 10,000 kilograms this vessel weighs. We then watch it fill up with water, and you see something like this. You watch it fill up with water, and then because our liquid level is constant, every volume of sand that comes in kicks out the same volume of water. Sand is 2.65 specific gravity. Water is 1 specific gravity. So we can take that weight difference, attribute it to sand production, and kick out something like this for our clients real time, which is an increase in total weight over time, computed to a percent full over time. So you see it 0% full here. And as the weight comes up, that's sand. When we get to 50 or 60% full, they shut it in, which pressure goes to 0. This is the pressure curve. Pressure goes to 0. Clean out all the sand. And now you're starting over. And this allows them to have the data of how many pounds of sand they're making, when they're making it, what the velocities are when they make it, to try to refine their processes. And that's how our client got to that 1 to 3%, is they took that data, put it back into their completion programs and their production processes, and said, we can tweak things here to get that number now that we can measure it. So this is something that no one else in the industry can do, and really takes a company thinking like engineers, not just in the field putting wells online without looking at what they're doing. So this is what we give for our clients, and it's part of our value to them. Does that make sense to everybody? How we get it done? Yeah?
You said you will shut off the wells when you clean up this. So can you use two there? So you can switch them, but you don't need to shut off the well.
Right.
Is that not possible for the industry?
Right. So taking that a step backward, we have clients that don't care about shutting in the wells. They're okay to shut them in for 40 minutes. They don't think that affects the reservoir. We have some clients that think that that's descents. Every time you shut in the wet reservoir, you reduce its production capability. So, and everywhere in between. So in cases where you do not want to shut in the well during the clean out, you can either bypass through a different sand protection solution, one that might be less suited to extended periods of time of protecting yourself from sand. A Y strainer, so basically a screen put in a bypass line. That's what was going on up here. You see where it's bypassed. So when we would clean out the well, we would isolate it here, isolate it downstream, and then they just bypass through this line here and through a Y strainer. Or we would do not 2 on 1 well, because that's costly. We would put 3 on 2 wells, so that now you're piping through a bypass unit. And we proposed that to several clients. No one's bid on it yet, but I think that makes a lot of sense in a less cost-conscious environment. Right now, it's tough to sell 3 units on 2 wells when 2 units is really all you need. But operationally, that can be done. And, you know, part of what we do is work around the objections we get from clients. We don't want to shut in our well. You know, we don't like the labor of cleaning it out. You know, we try to come up with real-time solutions to make that make it an option for them. Okay, so we'll take a mini technical break and talk about Rick, who's the U.S. operations manager, who I said was hoping to be here but had to go on a family emergency to Washington, D.C. He graduated with a geological engineering degree and also signed on with a service company. He focused on the logging part of the process and did logging processes in several parts of the world: Texas, Scotland, in Salah, Algeria. I think it's the hottest inhabited place on the planet. Like 120 degrees. It's like third winter. But yeah, it's crazy to hear talk about how he survived that. But that field engineering aspect allowed him to be a part of trying a lot of new technologies, put him on the front lines of running jobs in the field. And he would say as well, you know, getting that field experience sets you up long-term for your career. He had 7 years of it where I only had 1.5 or 2. So, yeah, definitely the service company, that's something you're going to get. Operators are going to put you into a team. They're going to get you a lot of experience. You know, working with other engineers, it may be different. I'm sure their training programs are differently tracked for some field, but not as much, being that that's not what they're expecting you to do on a day-to-day basis in the short to medium term. He also got his MBA and was told to start operations in the U.S. They've been operating in Canada for 10 years, comfortably, happy. All the Canadians love working in Canada with all their friends. They were bought by a private equity firm who said, you need a U.S. footprint because when we're going to sell you, they'll probably be to a U.S. company and this will make you more valuable. So they went and looked at all the different areas of the U.S. that were similar to Western Canada. Here in the Northeast, you had similar geology, similar rates, similar frac jobs, and most importantly, you had environmental sensitivities that were similar. In Texas, having an uncontrolled release of fluids or whatever, it's a problem, but it's not the months and years of paperwork and depositions and all the rest of it that it would be in Pennsylvania or down in New York. So the U.S. is where we chose to start our U.S. footprint, and that happened 2 years ago. I came on board with them about a year ago. So back to the engineering part. I don't know how I'm doing on time. But, the challenge became, how do we figure out where the first sand grain is going to land on the bottom of the desander? So the sand starts, we'll call it up here, so we have a worst case, even though it's probably somewhere in here. But we'll call it here. And gas is going to move through at one velocity. Liquid's going to move through at another velocity. And sand is going to fall at a given velocity in gas and a different velocity in liquid. So how do we figure out where that first sand grain is going to fall? Well, the first thing we need to do is figure out the cross-sectional area of the liquid and the gas so that we can figure out the volume at that instant and figure out how far you have to fall to get to the bottom at every point along this 20-foot vessel. Doing it on a tilted unit becomes even more difficult because you now have the bottom getting lower. With every foot you go, the bottom gets lower. With every foot you go, velocity in the gas phase gets faster, and the velocity in the liquid phase gets lower. So now it's a dynamic problem that, had we remembered calculus, we probably would have used it. But instead, we took it on a piecewise method. So how would you figure out the area of the liquid at any given point in the pipe? I'll go back over here so you guys don't feel left out. So you have this pipe. It's full, say, to that line. The radius is about we'll call it 7.5 inches. Height, the fluid here, we'll say is 13 inches. I think that's all you need to solve. The idea is where you start. Some of the hints are up there on the slide.
You have a half circle, and then you have to do.
Right. So basically, you're talking about the central angle theorem. So you have a radius, looks like that. Figure out that theta times 2 gets you this angle, which allows you to figure out this base. So now you're going to do a percentage of the circle times the entire circular area. And you're going to add this triangle to that. So, I don't know how we're doing on time. I guess I won't go through it, but this is how we started.
You have 20 minutes left.
Okay. Maybe we'll go back into it. That's just where it started, right? So now that we have this cross-sectional area, we broke the vessel into 100 pieces. So 1/5 of a foot slices. And each 1/5 of a foot had a particular volume of gas in it and a particular volume of fluid in it. And when you determine that, you can determine that velocity by the volume of gas that's coming in, going through that section, goes through a particular velocity. We then were able to use the ideal gas law to create a multiplier. And so your ideal gas law, PV equals N RT, something like that, said that our pressure was constant. The volume going through, the volume of gas going through each section was constant. The temperature is constant. What does R stand for? I don't remember.
If you
What's that? It's a constant, okay. And then, so then what you're talking about here is, the only difference is you're going from one volume to a smaller volume. The proportion of that volume should be the same as the increase in velocity. So one of these columns